Welcome to lecture review 1B, and this will take us up to the end of integration. This is just an itemized list of the slides to follow. I'm not going to go through this slide in any detail, and we'll move on to the next slide. All right, so the first thing we looked at in integration was just double integrals over rectangular regions, and there's a theorem that, of course, applied for that. And so if you look at this, we basically said that we could essentially write a double integral in an iterated form, which means that we basically interchange dx dy. So here, x would relate to limits between a and b, and y would relate to limits between c and d. If you switch these around, then of course these would have a different ordering sequence. Here are the limits for y between c and d, and the limits for x between a and b. So this is the way the book states it, but there's a geometrical interpretation because effectively a region is bounded by lines. And so it's understood that if it's a two-dimensional object and you're saying the limits on y are between y equals c and y equals d, that means x can be anything. So if y is varying, that means we have two horizontal lines. Similarly, x is ranging between a and b, but y can take on any value. So if y can take on a value, that means it'd be two horizontal lines, a and b, vertical lines and horizontal lines. So this is what this is basically trying to indicate. So x is constant here, y is constant here. If x is constant here, we're talking about two vertical lines. If y is constant here, we're talking about two horizontal lines. So that's more or less how you interpret it. So four lines, basically will bound a region, or we call that an area. All right, then we went and expanded and extended this to general regions. And so when we talk about general regions, means, for instance, if we were to integrate with respect to y followed by x, that means that this would be some lower function g of x and some upper function h of x. This function will be assumed to be larger than this one. And so these would represent curved lines, two curved lines. And in this case, y would be being held constant. So if y is being held constant, that basically, in this case would be just h is function x and g is a function x. Here, on the other hand, x basically is held at value a, lower limit, x is a value of b, upper limit, y can take on any value. So if y can take on any value, this would represent basically two vertical lines. So x equals a, y can be anything, and x equals b, y can be anything. Now you could also do a iterated integral, which means you reverse the order, dx followed by dy. But here now we have to be careful, because once you do this, x will now have to be a function of y. So g is a function of y, be a lower limit, h and y is an upper limit. And the limit on y would be between some value c and d. And so you can see that this and this basically have no relationship to each other. If these were constants, we could swap these two. But in this case, when it's general, we cannot do so. Anyway, this is just an explanation as to basically the fact that we're dealing with lines. Two curved lines, two straight lines. All right, so next thing we looked at was triple integrals in Cartesian coordinates. And so the simple case is between constant bounds. So for instance, z1 to z2, y1, y2, x1, x2. So this is the inner integral, this is the middle integral, this is the outer integral. And so in that order. So what does this represent if we're dealing with Cartesian coordinates? z2 and z1 is between two planes. So if z is held fixed, and x and y can be anything. And so the two yellow planes correspond to the inner integral. The y represents the two held constant values of y. Here's one value. Here's another. This is the upper bound. This is the lower bound. And x and z can take on any value. And finally, the outer integral between x1 and x2. And that corresponds to holding x at one value and an upper value. So this is the upper bound, this would be the lower bound, and this would be two plates or two planes which are parallel to the zy plane. Now if you look at this, right, you see basically 6 surfaces. These 6 surfaces bound the volume, and so that volume is contained within this intersection set. You can't see it here, but that's effectively what we've done. Surfaces bound the volume. If you basically go to the general case, then you can see here that on the integral, this would be 2 curved surfaces. This curved surface will be at a higher point with respect to the z-axis compared to this one, and it'd be a function of x and y. The middle integral would be h of x upper bound, g of x lower bound, but y and z have not been specified, which means they can be anything. And so this would represent 2 curved planes, not flat planes, but curved planes. And x between a and b, x equals a, x equals b, means y and z can take on any value. These would be 2 parallel planes, but basically at value of x equals a and value of x equals b, and that means these planes will be parallel to the yz plane. And so this is basically how we would do it. If we were to do an iterated version of this, that means change the order, then all of these would have to change. So for instance, if we had y first, then this would have to be a function of x and z, and this would have to be a function of x and z, and so on. So this is basically what we meant by the interpretation of triple integrals in Cartesian coordinates. All right, then we sort of looked at what happens if we end up with complex integrals, and we were wondering whether or not it would be possible to find a simpler way to solving an integral, and that would be by means of changing variables. Now you've done this in Calc 1 last year, and that was for the single variable case where you just change variables. Now we generalized it to the case of multivariables, starting with double integrals. And so this was one of the theorems that came up. We have a transformation that basically says let x be some function of u of v and y be some function of h of u and v. And so this becomes basically one-to-one within the domain that is bounded by some form of boundary. So we were able to say that if we want to integrate f of x, y dA, that's equivalent to basically putting x in terms of u and v, y in terms of u and v, but dA now basically gets transformed according to the absolute value of a Jacobian, and the Jacobian will show in a second, dA, where this dA now relates to the new variables u and v. Now we need an inverse transform, that is u in terms of x and y and v in terms of x, y, because it's useful to describe the boundary in the UV plane. Not only do we have to basically revise the differential area, but now the bounds on the surface are going to be in terms of variables u and v rather than the variables x and y. So the Jacobian, this j that we see in here, is nothing more than just taking the determinant of this matrix, where the matrix elements are just the partial derivatives of the transformation. So dg by du, dg by dv would be the first row, and dhu and dhv would be the second row, and we take the determinant of that. Basically, that's the Jacobian matrix that we're dealing with. Now, we mentioned in previous lectures that we put an absolute value here. Well, the reason that is done is because depending on how you define x and u, you could have defined x to be h of u and y to be g of u. So that would mean that this determinant under those circumstances would become negative. Well, we know that results have to be positive. And so the easiest way to do that is to put an absolute value here so that you don't basically make the mistake of reversing the order. The only thing one can say for certain is that if you've chosen a right-handed coordinate system, chosen this correctly, then the result you will get will always be positive. In other words, the determinant will be a positive entity. But just in case you make a mistake, you just take the absolute value. All right, so then the question came up is, well, how do we choose variables? Well, one option is the variables, the new variables or change of variable transformation is given. Sometimes the change of variables is determined by the 2D region. So just by looking at the region, it suggests a transformation. And sometimes the change of variables is determined by the nature of the integrand. So sometimes you can find a very simple way of changing the integrand so that the function looks easier. So there are these different techniques basically that one can employ, and we looked at a number of them, but in a very general case, it would be a very difficult problem to solve. One wouldn't know in advance what approach to take. All right, so then the simplest change of variables for for double integrals was polar coordinates. And so here we basically would be looking at a polar coordinates would mean x equals r cos theta, y equals r sine theta. And for the simple case where we just have constant bounds, r would have a limit, upper limit of b and a lower limit of a, and the angle theta would have a lower limit of alpha and upper limit of beta. There would be some restrictions because r can be only greater than or equal to 0, and the difference between beta minus alpha should be less than or equal to 2 pi. So if we were to look at an interpretation of this, then you look at the diagram below. This would be the more general case where we don't put restrictions on the upper and lower limits on these integrals to be constants. So for example, here we have an example for where the lower limit is a function of theta and the upper limit is a function of theta. Of course, the outer bounds will always be constant values, so this would be angle alpha and angle beta. And so if you had some function f of xy, then the x will be replaced by functions of r theta, y be replaced by functions r and theta. And so in compact form, you end up with this expression here. Again, here are the transformation vectors, transformation equations. So how do we interpret the region when we have something like this? So we come over here. If theta equals alpha, that just means it's a straight line where r can pick any value that's greater than or equal to 0. So it extends to infinity. At theta equals beta, r starts at 0 and extends to infinity. So these are two lines that are bounding the region. And you have this curved line, which would be r equals h of theta, which is the upper bound on the integral, and r equals g of theta, which is the lower bound on the inner integral. So these four lines, two of them curved and two of them straight, bound the region. And so that's how you quickly can sketch what the region would look like. So let's do an example, and this is from chapter 16.3, question 15.1. The question is, use a double integral to find the area of the region inside both the cardioid r equals 1 plus sine theta and the cardioid r equals 1 plus cos theta. And so I've got a little simulation to show you what this looks like. I mean, you can more or less sketch it out just in stages. You know basically that you have x equals r cosine theta, y equals r sine theta. R basically gets replaced by this function or this function, depending which cardioid you're interested in sketching. And so for the case of the blue cardioid, that's the one which we call r equals 1 plus sine theta, we'd be sketching out this particular heart-shaped object. If we're dealing with the red one, which is r equals 1 plus cos theta, then we'd be sketching out this one here. All right. Now what this diagram shows is our position vectors for the red, the blue, and the intersection set. So the blue is all of this, the red is all of this, but the intersection set is this region, and this tiny little sliver that you see right here. Okay, so you have a position vector that will trace only the blue one that traces only the red one, and one which does the intersection set, which basically means that it would start here, go like this, around like this, around like this, and back to the starting point. Now, if you look at the object, you'll see there's a certain symmetry. If I were to draw a straight line from the intersection point between the red and the blue cardioid here, it intersects here, and it intersects here. So there are three intersection points. If I draw a straight line through that, then you'll find that everything to the left of the line or everything to the right of the line basically are mirror images of each other. They're the same. So it's useful to know that because this is how we're going to set up the integration. Now, these sliders basically are indicated here, t being the blue cardioid position vector, q being the, p being the red cardioid position vector, and q is the one that traces out the intersection between the red and blue cardioid. If you want to know the length of these lines, this one here versus this one here, in the first quadrant it takes on this value, in the third quadrant it takes on this value. So this is more or less just sort of the setup for the problem. Okay, so now there's a problem here because the region of interest cannot be described by a single integral since the boundary enclosing the region consists of two piecewise continuous curves. So the intersection set, basically, if you go along here and along like this is one continuous curve. And this is one continuous curve. However, if you go from here to here, you can see that the slope suddenly changes. So this basically is not going to be a continuously differentiable. And so what we need to do is take this as one region, and this is a second region. And so we have an integral for this region and integral for this region. So we need to know what the limits on that integral will be. So r, we know, goes from 0 to 1 plus sine theta. This would be for the blue cardioid. And r goes from 0 to 1 plus cosine theta for the red cardioid. And so when we're going around, for instance, for this portion here, we'd be looking at portion of the blue cardioid, and this would basically be the dividing line. For this section here, we're talking a portion of the red cardioid. So this would be the upper part. We also need to know what's the starting points and the finishing points. So for example, for here, this starting point, this occurs when these two intersect at some angle here. And then again, there's an intersection at some other point. There's an intersection point here. So how are we able to do that? Well, basically what we do is we equate these two to figure out at what values intersection takes place. That corresponds to three different values of theta. One for here, one for here, and one for here. So this one corresponds to theta equals minus 3 pi by 4 because the angle's with reference to the x-axis. So minus would be this way. You have theta equals pi by 4, which is to here. And you have theta equals pi by 4. So theta pi by 4 would basically take you from here all the way around to this point over here. Okay? So now we can basically set up the integral. So for the blue portion, which means we're going from here, around here, to here, that's from minus 3 pi by 4 to pi by 4. And for the red portion, going from here, to the other side, will be from pi by 4, and eventually we make it to 5 pi 4, which is over here. That's going from here around to there. The bounds on r would be from 0 to 1 plus sine theta for the blue portion, and 0 to 1 plus cosine theta for the red portion. So if we sum these two together, and finally you'll end up with an answer of this form. And it turns out this value and this value will be identical to each other because of symmetry. If you look at this, you'll notice that these two basically are identical to each other. Anyways, this is the approach that's taken to solve this particular problem. You do have to break it up. Just be aware of it. Sometimes it's not a single integral, but you may end up having to have multiple integrals because you have to break it into subregions. All right, so when we go to the triple integral case and we change variables, we only looked at two particular cases, namely cylindrical coordinates and spherical coordinates. So in cylindrical coordinates, we basically end up with the differential volume element being r dr dz d theta, and r represents the Jacobian. The transformation equations are given here. R, of course, is going to be greater than or equal to 0, and it's parallel to the xy plane. Theta ranges from 0 to 2 pi, and z is just an element of r. So in this case, if we're dealing with constant boundaries on the integrations, the inner integral, middle, and outer, if it's basically from one value of r to another value of r, that means that we're talking about an inner cylinder and an outer cylinder. So these, don't forget, are now surfaces, but it's a cylindrical surface. Z1 to Z2 would be two plates, two parallel plates, basically sitting at different values of Z. So these are two yellow ones. And theta basically is going to be the angle And the angle basically is with respect to the x-axis. And so this would be this would be a vertical plane, right, which rotates about the z-axis. And so this angle in here would be the angle theta. As this advances, then the value of theta advances. So this looks like wedge segments of a pie. One could be here, and at different theta, there would be another one here, which is the one you see here. So that's basically how to interpret it. And so the domain of interest would be everything that's contained between those two plates, and between those two cylindrical surfaces. That's basically the region over which the integration is taking place. So let's do an example. And so this is a problem statement. You're given a region. Here we put everything in terms of inequalities. And you want to calculate this particular integral in Cartesian coordinates and then in cylindrical coordinates and compare the two approaches. Right? The comparison will be done at the end after we've discussed this, the calculation in cylindrical coordinates. All right, so first thing to do is to figure out how do we take these results here and write them out in a form where we can establish what the boundaries are. Well, if you look here, for instance, you need an upper surface in red, and we have a surface here, which is the lower surface, that x equals 0. So an upper surface here and a lower surface here. How do we get the upper surface in red? Well, you get it from this condition, x being greater than or equal to 0, and x squared plus y squared equals z squared plus 1. So these are basically these surfaces. And notice here, this is not the standard way of showing coordinates. This is the simplest way of basically solving the integral in Cartesian coordinates. Again, it's a form of iterated integral, where in this case, x is pointing upwards, y is this way, and z is this way. The labeling is such that it's consistent with a right-handed convention. So there's no issue there whatsoever. So in this case, we would represent x as a function of y and z. And of course, x is greater than or equal to 0, which means we only care about this surface. This will have two solutions, x positive, x negative. It's only the positive solution we're interested in. The blue surfaces would be between z equals 0 and z equals √3. So here's one surface, just a cut out of it, and this surface here. And the two side surfaces, which you sort of see here, but probably you should click on this link, and then you can see it a little bit better. There's one on this side and one on the back side, right? And that would be established from y squared equals x squared z squared, which means if you take the square root, you'll have two possible answers, plus and minus. So in this direction and in that direction. So more or less, this is how things are set up. And of course, if you were to look at the region of integration, then it's a projection of this onto the onto the zy plane, and it turns out that projection is more or less looking like a triangle. So knowing that, then the question is, how do you solve this in Cartesian coordinates? Well, again, this is a problem where effectively we cannot do it in one go. We have to break it into two subregions. And so what we ended up doing is putting a vertical line through here and splitting this into two half sections. So we're going from here to there and from here to there. And so that's effectively what I've done here, right? You've got this basically as 1. This is between the z values. It's between these two plates. 0 to z. Okay, so this would be basically between this surface here and a halfway point. So like almost a vertical plane that's parallel to the xz plane. And then this is between the surface 1 minus y squared plus z squared, which is more or less the top surface, and the lower surface, which is from here. So we have this, and then this would be the other side, from here over to the other side. Well, you can do actually, this integral can be done. It's more or less straightforward, not too complicated. So when you take the sum of these two, ultimately you're integrating from 0 to √3 of z squared plus 1 dz, and this turns out to be 7/3. So it's doable, but essentially you need to make use of these diagrams to at least understand what the domain looks like. On the other hand, if you do it in Cartesian coordinates, you probably don't even have to draw the picture. This becomes almost straightforward, and it can be done in a single integration. So right away you realize two things. One is you can get away without drawing it, and secondly, it can be done in one go. So again, here are the limits that we're dealing with. the different inequalities from which we obtain basically the integration bounds. So again, in cylindrical coordinates, these are the transformation equations. And we basically have to make use of these inequalities to determine the 6 boundaries. So for the bounds on Z, it's pretty straightforward. It's given. Bounds on R, we have to convert the equation x squared plus y squared less than or equal to z squared plus 1 into cylindrical coordinates to obtain r squared is less than or equal to z squared plus 1. All right, so therefore the bounds on R are from 0 to square root of z squared plus 1. R has to be greater than 0, so you can only basically consider the positive square root. So the last thing is the bounds on theta. So here what we have to do is to factor the third equation, which is this one here, and make use of the fact that x is greater than or equal to 0 and z is greater than or equal to 0. So we have this information and this information. So we end up with y squared minus x squared z squared is less than or equal to 0. You can factor this out as y minus xz times y plus xz less than or equal to 0. And there's therefore 2 possible solutions, but only one makes practical sense. So either have y minus xz less than or equal to 0 and y plus xz greater than or equal to 0. That's basically one option. The other option is y minus xz is greater than or equal to 0 and y plus xz is less than or equal to 0. The former is the correct one, from which we obtain minus xz is less than or equal to y is less than or equal to xz. Okay, and so that's basically making use of this expression right here and just putting it in a more compact form, where now this is sort of like, looks like a lower bound, this looks like an upper bound. So the next thing to do is to substitute the transformation equations for x and y in here and divide all sides through by r cosine theta to obtain minus z less than or equal to tan theta is less than or equal to z. Or if we take the arctangent of this, then we see theta here. This is the lower bound and this is the upper bound. So now we're ready basically to put all the pieces together. The volume element here in cylindrical coordinates becomes r dr d theta dz. We have to substitute for x in terms of cosine theta, r cos theta, and similar x squared plus y squared. And so when you compute this, you end up with just cosine theta. And so the limits now will be basically the limits on r, upper bound, lower bound, the limits on theta, lower bound, upper bound, and the limits on z, lower bound and upper bound. If you go through this calculations, lo and behold, you get the same answer. But this is so much easier because you could get away without having to graph it, and at the same time you could do it in a single integral. If you want to look at it in terms of what it looks like, here's the diagram to show for it. So r basically would be this one. We can scan around like this, and theta basically would be like this. So this would be for, this is with respect to the xy plane. So you can see this would be moving in a positive direction. So this is a positive, and this would be negative. And so this is basically referring to these limits that you see here. All right, so the last thing we looked at was spherical coordinates. And so this basically is the picture that we need. Here are the transformation equations. Rho in this case is going to again be is greater than or equal to 0, only positive. Phi takes on a maximum value from 0 to pi, and theta is between 0 and 2 pi. If we sketch this out in the form of surfaces, then on the integral, inner integral, it's between two spheres with different radii. So that's what you see here, the blue. The next is between phi 2 and phi 1, which represents cones, right? Phi basically is an angle that's measured with respect to z-axis. So if phi is held constant, it means theta can take on any value and r can be any length. So you see one cone here and another cone here. Lastly, you have theta. So theta basically is just a vertical half plane. And so the orientation of this half plane basically changes depending on what this value of theta is. So these are the two surfaces, two surfaces, two surfaces. The domain of interest is basically the intersection set between these 6 surfaces. The Jacobian is this term that you see here. It's rho squared sine psi. So this is the way we would typically set it up if we're dealing with constant terms. So the last thing to do is an example. And so here basically you're given to write a triple integral in spherical coordinates to calculate the volume of the region below the top sheet of the hyperboloid, which is this blue object, which is given by z squared equals x squared plus y squared plus 3. Or if you want to express in terms of z, it would be the positive square root of x squared plus y squared plus 3. And above the cone z equals square root of x squared plus y squared, which is this gray object that you see here. Note these two objects in the limit that x and y approach infinity intersect. So if you go far enough away, these two eventually basically will coincide. If you want to look at it in more detail, you can go to this URL here. All right, so again, we make use of spherical coordinate transformation. Here they are. And so we need to understand the domain, which means first we need to figure out what the bounds are, starting with the bounds on theta. Well, if you look at the diagram here, it's clearly that it's symmetric. And so theta will just go from 0 to 2 pi. It's full circle. Bounds on phi, the range of phi can be computed by plugging the spherical coordinate transformations into the equation z equals square root of x squared plus y squared. So that means you take this, plug it in here, you take this, you plug it in here, and you take the z term and you plug it in here. If you simplify, you end up with an expression tan phi equals 1. And from this, it's obvious that the bound on phi will be pi over 4. And so pi over 4 basically is measured from the z-axis, so from here to there. So that actually is the cone. Okay. The lower bound on phi will be 0. So basically we're sweeping from here all the way down to here. So that means the range on phi now would be from 0 to pi over 4. So the last thing is the bounds on rho. The upper bound limit on rho is obtained by plugging the spherical coordinate transformation into the equation z squared equals x squared plus y squared plus 3 and simplifying. So if you take the z term in here, the x term, and the y, simplify, you end up with rho squared equals 3 secant 2 psi. The lowest upper bound on rho is root 3, which corresponds to basically a vertical line. That's when phi equals 0. The largest upper bound on rho is infinity when phi equals pi, which is over here. This is when this basically goes out to infinity. So the integration bounds for rho will be from 0 to square root of 3 secant 2 phi. So now that we have the bounds, we can just plug them in. And of course, we need basically the Jacobian because we're going to look at the volume. So the Jacobian is rho squared sine phi, and then this then becomes the differential volume element in spherical coordinates. So that completes Review 1B lecture. Thank you for listening.